So, welcome here again. Today we will start with sampling. Today we will talk about sampling methods, but before that we will review some of the lecture, some part of the lecture from yesterday, just to remind you what we did yesterday. Okay, thank you.
Okay, yes, so I'm going to start off with just a review of Gaussian processes to reinforce the idea of what a Gaussian process is. Okay, so we said a Gaussian process prior defines a prior over the space of functions from our input space X to R. Sorry, can you see over? Maybe I can just move this over a bit. No. I think that it'll just slide over. Okay. Okay, so we said it's a prior over functions which go from our input space to the real line. We can think of a Gaussian process as an infinitely long vector of random variables, and any finite subset of these random variables have a Gaussian distribution. So we have this collection of random variables here, which in general is uncountably infinite. And we say that if we take any finite subset, so if we take any x1, xk, for xi in our input space, and any natural number k, then f of, just let x bar denote this vector here, then f of x bar has a normal distribution with some mean and variance. So the parameters of the Gaussian process are the mean function, which is a function from our input space x to the real line. So the mean function is just equal to the expected value of the random variable f of x for any x in our input space. The second parameter is the covariance function. So this is a function from x by x to the real line. So we can say if we take any two inputs, x, x1 say, and x2, for xi in our input space x, then the covariance function is just equal to the covariance between the function at x1 and the function at x2. Okay. So we saw that typically the mean function is chosen to be equal to 0, and different covariance functions imply different properties on our samples from the Gaussian process prior. So we saw some examples of different types of covariance functions. Most of our examples were stationary covariance functions. We did actually see one example of a non-stationary covariance function. That was in our example where we saw what the Gaussian process prior was induced by the linear regression setting. So in that case, we had a covariance function of this is an example of a non-stationary covariance function. And we also saw how to extend this setting so we can have other properties such as periodicity and how to extend it to a multivariate setting. So we also saw how to sample from a Gaussian process prior. So how we do this is we just specify an input grid of x's, and then we just take a sample from a multivariate normal. So say here's some realizations of a multivariate normal here. So this is f of x. So now suppose that we wanted to have additional samples of the function, say x1 star, x2 star, xn star. How would we do this? So if we've already sampled f at x, how do we sample f at x star, given what we've already sampled? So this is just a multivariate normal. We just use the properties of the conditional property of the multivariate normal. So we know that jointly f of x and f of x star are normal with mean m of x and m of x star. And the appropriate covariance matrix. So we know that the conditional of f of x given f of x star given f of x is just a normal with a mean that is linear in f of x and a covariance matrix. So we saw yesterday in the slides what the equations were to compute these terms here. So in particular, if the mean function is 0, the intercept drops out. This beta 1 is just sigma 2, 1, sigma 1, 1 inverse. So in that case, this is sigma 1, 1. This is sigma 2, 1. And sigma 2 given 1 is just sigma 2, 2 minus sigma 2, 1, sigma 1, 1 inverse, sigma 1, 2. Okay. Sure.
How do we know that f of x star given f of x is this multivariate normal?
So this is the conditional property of the normal distribution. So we know from the definition of a Gaussian process that jointly they are normal, correct? Because if I take any finite subset, so if I extend x to be x1 to xn and x1 star to xn star, then we know that jointly these are multivariate normal with this specification here. So we just know from the conditional property that f of x star given f of x is also normal. So we can get additional samples at our new points. And what is typically done in the pictures I was showing you is people just kind of connect the dots there to get something that looks like a function. But in reality, we can't actually sample f of x at every x in x, because this is generally uncountably infinite. Okay. Sure.
So this is a general property of random functions that when we think of random functions, that we sample random function at once at all the points we are interested in. And then if you want to work like sequentially with the functions that we have set, then we have to do it, this is a more complex thing than doing this. These sort of general functions, if you had different random functions which would follow different properties, would do it the same way?
So if you use a different prior here instead of the Gaussian process prior, yeah, well, the nice thing about the Gaussian process prior is that it has this conditional property here. So if you have a different prior, then you might not have this conditional property here.
But if you wanted to define the prior differently, you define it the same way, again, at all the points at once.
Yeah. So you can use this for basically any family of distributions. You can think of defining a prior on a function with any family of distributions, but you need that this family satisfies, in particular, it needs to marginalize. So when we saw the Kolmogorov extension theorem, so we can specify the collection of marginal distributions for any finite subset of x. And in order to induce a prior on a stochastic process here, on our function, we need that marginalization property to hold.
So is it like when you have the Dirichlet process and we define the Dirichlet process as a prior on the probability distribution, which is a function?
Yeah, so when we'll see that. We'll see another example with extending the Dirichlet distribution to a process there.
And the reason to do the f star differently than the x star differently than x is because it's computationally simpler, or why cannot you got in some way fx, and then you want more? Why don't you get the same way you got the fx in the first place?
So
you sampled somehow.
Okay, because that would be a new sample from our prior. Okay. So here I want to say I want to continue the realization that I had before. So in general, if I took another sample, another realization, I might get something else.
Okay, yeah.
Okay.
This would be a way to refine the rate of x.
Yeah. So this would be, so if you had sampled this and you wanted your sample evaluated at a finer grid, you would go through this. Okay. So if we use the Gaussian likelihood yesterday, we saw that so this is the Gaussian likelihood. What makes GPs so nice to work with is that they're conjugate to this Gaussian likelihood here. So the posterior is a Gaussian process still. So F given our data is still a Gaussian process with updated mean and covariance function. So in general, if I use a different likelihood here, then my posterior will not be a Gaussian process. And in that case, I will need to resort to sampling methods or approximation methods in order to obtain posterior inference on my function here. So today we will see some sampling methods. So an example of this is, suppose y is just binary. So it takes values in 0, 1. So we could say y given xi and f is Bernoulli with some probability that depends on x. So one way we can model this probability is, so this probability is just the probability y is equal to 1 given x and f. So we can use some link function. So f here is a Gaussian process, and L is just some link function which maps the real line to the interval 0, 1. So it just squashes our Gaussian process so that it takes values in 0, 1. So if I use this likelihood here, instead of the Gaussian likelihood, I no longer have this property of conjugacy. So in this case, we need to use sampling methods or some of the approximation methods that.
In this case, would it be sufficient to choose the conjugate prior for the Bernoulli distribution in the definition of GP and substitute out the n by the conjugate prior?
So in general, there is no conjugate prior in this setting. So if you look at the just the simple linear case, so if we have some link function, we want to say that this is a linear function of x. There's no conjugate prior for the weights w.
If we didn't have the Bernoulli distribution, if we had something which has a conjugate prior, then could we do that and still expect?
So the Gaussian process, the thing is that so just think in terms of the linear model that we had here. The Gaussian distribution on the weights was the conjugate prior to the Gaussian likelihood. So if we use a different likelihood, in general, the conjugate prior will not be Gaussian. So we would need a alternative prior there to have conjugacy. Does that make sense? Okay, so let's go ahead and start with the sampling methods. Are there any other questions? Just erase. So I encourage you to try to sample from a GP. It's really easy. It takes 2 lines of code to write up. It'll give you some practice on what these things are. Okay. Okay, sampling methods. So in this setting, our aim is to compute the integral of some function g with respect to a density p. So that means we just want to compute the integral of g of x times p of x, where p is some density on x. So one solution is just to take a finite grid of x and evaluate the function and the density at each of these grids. So here's an example. The red line is our density p of x. The black line is our function g that we want to integrate, and we're just taking a grid of values, evaluating both the density and the function at these grids, and then we can estimate our integral. The problem with this approach is that the number of grid points needed grows exponentially with the dimension of x. So an alternative solution is the Monte Carlo method, which instead of taking a grid of x values, so you can see here that if we take a grid of x values, we get x's which have probability close to 0. So instead we can sample x's which are identically distributed, independent and identically distributed with density p, and we can approximate this integral by just plugging in our sampled values to the function and taking the average. So here we get, we no longer have those points with practically 0 probability. Properties of this Monte Carlo method: it's unbiased. That just means that the expected value of our estimator is the quantity that we wanted to estimate. It has nice convergence properties. So our estimator converges to the thing that we wanted to estimate as t, our number of samples, goes to infinity, and this holds with probability 1 almost surely. And this just follows from the strong law of large numbers. The variance of our estimator, so this is if our function has finite second moment, then the variance of our estimator is just the variance of our function divided by the number of samples. So notice that this variance here doesn't depend on the dimension of x. So in general, our approximation error will be independent of our dimension of x. But how do we generate random samples from our target density p of x? So the first solution we'll look at is the probability integral transformation. So this says is that if I have a random variable which is distributed according to f, if I define u equal to f of x, then u has a uniform distribution. And conversely, if I define x equal to f inverse of u, where u is uniform, then x has distribution f. So f inverse here is a generalized inverse. So what this is saying is that, so suppose this is our cumulative distribution function that we want to sample from. So here's f of x, and here's x. So to sample from this cumulative distribution, we just take, so this is 1, we just take a uniform random variable u, we sample a uniform random variable here, and we take the inverse, and we get a sample x from f. So that's described in this procedure here. The problems with this method is that we need to compute the inverse of f, which can be expensive or often unavailable. So let's see an example of this. An example is if we want to sample from a truncated normal. So in this case, let's see, what did I do with the eraser? So in this case, suppose we have this is the distribution function of the normal distribution. We can sample from a truncated normal, say truncated at 0, by just sampling. So this is f of 0, which for the standard normal distribution, for a normal distribution with mean mu and variance sigma squared is just given by that. So we just sample a uniform random variable in this interval here, and then we can, again, take the inverse. Okay, so here's an example of sampling from a truncated normal using this method, this algorithm. So here, mu is equal to 0. The variance is 1, so this is just standard normal truncated at 0. Some other problems with this method that you'll notice in the normal distribution case is that if mu, say 0 lies here, so mu is maybe -5 or something, then you may have numerical difficulties here because it may approximate f of 0 close to 1. Okay, so let's see an alternative method. Alternative method is rejection sampling. So our target distribution that we want to sample from is P of x. Q of x is a proposal density that can be easily sampled from, and such that P of x can be bounded by Q of x divided by some constant alpha, which is between 0 and 1. So the rejection sampling algorithm proceeds by we sample x from our proposal distribution, and we accept x, or our proposal candidate, x star, with probability alpha of x star, which is just the minimum of the ratio of P of x and alpha of x times alpha. So if we reject at this step, we go back up to step 1, we take a new sample from our proposal, and we continue until we accept. So the problems with this approach is that we need to find this proposal density that can be easily sampled and such that the number of rejections is small. So this alpha here, this gives us the expected proportion of candidates accepted. So let's just draw a picture here. So suppose this is P of x. We have Q of x here. This is Q of x divided by alpha. So we want alpha to be close to 1 as possible so that the number of rejections is small, which means that we want Q of x divided by alpha to be as close as possible to our target distribution. Another interpretation of alpha is that alpha inverse is roughly the number of steps it takes to accept a candidate. So let's go back to our truncated normal example. Another way we could sample from a truncated normal is by just using rejection sampling and having our proposal just be a normal centered at mu and sigma squared. So first, what is alpha in this case? Alpha inverse generally is the max over x of the ratio of P of x and Q of x. So for our truncated normal example, this is the max over x. P of x is, so let's suppose that mu is equal to 0, sigma squared is equal to 1. This is normal x 0, 1 times the indicator that x is bigger than or equal to 0, divided by our normalizing constant, which is just phi of 0 divided by 1. This is 1/2. And divided by our proposal, which is normal at x 0, 1. So in this case, you'll see that these cancel out. And we get that our acceptance probability, or the inverse, is 2. So our acceptance probability in this case is 1/2. And if we compute the acceptance probability of any x star, that's just the ratio of p of x over q of x. Times alpha. So you see these things cancel, and our acceptance probability is just the indicator that our proposal is bigger than 0. Sure.
What are the functions? So the idea is that we are taking just the positive values of normal distribution for the px, and we are sampling using the full.
Yeah, so what we want to sample from, let's draw a picture. So here is the, say, standard normal distribution. What we want to sample from is the truncated normal distribution. So we're just cutting off this tail here. And what's the mass of this? It's 1/2, right? So we just have to multiply, to renormalize, we have to multiply all these probabilities by 1/2. So this is the thing that we want to sample from, this density here. And in order to do that, what we're doing is we're sampling from the standard normal distribution, and we just accept it if we get something that's in the correct region. We reject if it's less than 0.
Okay, maybe I'll ask about the previous slide, but why we are doing the rejection, the truncating, the sampling. Like, what's the reason for the half?
Oh, this is just an example of. So this is just an example of a case when we can use. So we saw in the previous example that we could use the integral transformation to sample from a truncated normal. Now we're going to see how we can use rejection sampling also to sample from a truncated normal.
Yeah. I guess this is an example of non-trivial distribution from which you cannot easily sample.
Okay.
So we are not really much interested, particularly for this, but you are showing on this example, how you can sample from this distribution. You don't have a function in your toolbox, how to sample from it. Mm-hmm. So, in general, you will be probably interested in weirder, more complex functions you want to sample.
Yeah. And you may actually have something in your toolbox that samples from a truncated normal, but behind the scenes it does one of these algorithms to sample from it. So let's look at one other example here. I'll keep the example of the truncated normal, but I just want to change our proposal distribution. So instead of setting the proposal distribution to be a normal centered at our mean and our variance, let's consider, let's first set mu equal to 0, sigma squared equal to 1. And let's consider a proposal distribution, which is just the exponential with parameter 1, or gamma with parameter 1, 1. So if I use this proposal distribution, what is alpha in this case? So we can use the same, so let's redraw our picture here. Our exponential distribution is something like, say, this. So we need to shift it up a bit so it covers what we actually want to sample from, which is the truncated normal. So alpha inverse, we said that's just the max over x bigger than 0 of the ratio of p of x over q of x. So this is a normal 1 over square root of 2 pi exp of negative 1/2 times x squared over exp of negative x. And you can show that the max of this function here is when x is equal to 1. So if I plug in 1 here, I get 1 over square root of 2 pi exp to the negative 1/2 divided by exp to the negative 1. We get e to the 1/2. So that means that alpha is equal to the square root of, sorry, I forgot the normalizing constant here from the truncated normal. You should have a 1/2 here for the normalizing constant. So this simplifies to square root of 2 over pi. So alpha here is pi over 2 epsilon. So we said if we use the proposal with a normal centered at 0 variance of 1. So remember, our aim is to sample from a truncated normal with mean 0 variance 1. If we use this as our proposal, our expected acceptance probability is 1/2. Instead, if I use the exponential, this is my expected acceptance probability. So which algorithm would be better? Well, you can work it out. It would be this one. So this is square root of, or 1 over 4. And this is bigger than 1 over 4. Right? Oops. Okay. So let's just go back and look at some problems with this method. So in this truncated normal example, you can obviously see a problem. So if I use this proposal distribution, this normal, and say that the area that I really want to sample from is out here, then I will reject a lot. So ideally, you want to find this Q, which can be easily sampled from, but also that the number of rejections are small. So it can be difficult to find this proposal Q. And we can say the same with the exponential. So if our truncation was really here, and we wanted to sample from this region here, and we approximate this with the exponential distribution here, you can see that we will reject a lot in this case as well. So in general, it can be difficult to find this proposal Q. So let's see a third solution. A third solution is to generate a Markov chain, xt, for t bigger than 1, with an appropriately defined transition probability, such that for large enough t, our Markov chain is approximately sampled from our target distribution, target density p of x. Okay, so let's see what some of these quantities which I just said are. Just to review some properties of Markov chains. A Markov chain, first order Markov chain, over some state space x is a sequence of random variables such that the transition probability of going to state xt plus 1, given our past sequence of observed random variables, only depends on our previous state, xt. We say that it's a homogeneous Markov chain if this transition probability does not depend on t. The stationary distribution of a homogeneous Markov chain satisfies this property here, and a sufficient condition to ensure that p of x is a stationary distribution of the Markov chain is that it satisfies the detailed balance condition here for any states x and x prime. Okay, so why is that relevant? It's because if I have a x of t is a homogeneous Markov chain, and I have that the state space is the support, the state space is the support of our target distribution p of x. This Markov chain is irreducible and aperiodic. This irreducible basically means that I can go from one state to another state in a finite number of moves with positive probability. And aperiodic means that I don't require some period of states in order to get to that state. And it has stationary distribution p of x. We just saw what that means. And actually these two conditions are sufficient to show that this p of x, if it's the stationary distribution, that it's unique. And then from ergodic theory, we know that our Markov chain converges in distribution to a random variable x, where x has density, which was our target distribution, or the stationary distribution. And we know that the Monte Carlo estimate of the function g converges to the thing that we wanted to estimate. So our Markov chain produces, in general, dependent samples from our target p, and these can be used to estimate the thing that we wanted to estimate, g, here. So in general, what we'll do is we'll generate a large Markov chain, and we'll need to discard some samples so that we obtain nearly independent samples from our target density p of x. Is that clear? So how do we construct such a chain? This can be done through Metropolis Hastings. So the idea in Metropolis Hastings is to introduce some proposal density Q, which depends on our previous state xt, and we choose some starting value x naught, and in each iteration we generate a candidate value x star from our proposal, and we accept this candidate value with this acceptance probability here, which is just the ratio of our proposed at our target density p divided by our current value, and the ratio of the proposal density q. So if we accept, we set xt plus 1 equal to our proposed value. If we reject, we set the next state equal to our current state. And you can show that in this case, this is our transition probability of going to xt plus 1 from xt. So here this is, we generate a new value xt plus 1, we accept it with probability xt, or in general, we reject xt and we stay at our current state. So you can show that this transition probability satisfies the detailed balance condition here. So that's not too difficult to show. And so this means that for large enough t, we have that our samples are approximately samples from our target distribution p of x. So is that clear? Or, yeah. Sorry, can you repeat?
The delta. It's the last function.
Oh, this delta. So this is a Dirac measure. It has measure 1. It has all its mass at xt. So mass 1 at this point xt. So this thing is 1 if these two things are equal, 0 otherwise. So we can actually go through this. Maybe it'll be clear if we show that we prove the detailed balance condition in this case. So let's go back. This is our detailed balance condition. So we want to show that this holds for this transition probability. So we have the proposal, the probability that we accept our proposal, plus the probability that we reject, times the indicator that our candidate value is our current value. So this must be equal to this thing, just flipping the values of x and x prime. Okay, so first case, if x is equal to x prime, it's quite obvious that this holds, right? All of these values will be the same, so that this term will all be identical, right? Is that clear? So that's the first case. The second case, in general, if x is not equal to x prime, then this term here cancels. So we just need to show that these two things are equal, right? So let's look at this acceptance probability. Acceptance probability of x prime, given that our current state is x, this is just this quantity here. So if this thing, it will be equal to this if this thing is less than 1. So this will be equal to p of x prime over p of x, q of x given x prime, q of x prime given x, if this is less than 1. So that holds if okay, so if this is less than 1, then the inverse of this is bigger than 1, right? So the inverse of this would just be the acceptance probability if I flip these guys. So that means that this thing will be equal to 1. So now, in that case, if I plug in this here, I see that this denominator cancels with these two terms, and I just get that this is equal to these two things, and that is 1, which we just said. So the detailed balance condition is satisfied. And the reverse case is the same. So if this is bigger than 1, you can show the reverse analogously. Okay. So now, how do we choose this proposal density Q? So we'll look at 3 possibilities: the independent Metropolis Hastings, random walk, and Gibbs sampling. Okay. Okay, so let's start with independent Metropolis Hastings. In this case, our proposal density is independent of our current state, and our proposal density must satisfy this inequality here for some constant alpha. And in that case, our acceptance probability reduces to this quantity here, right? Our proposal doesn't depend on our previous state here. So this algorithm is very similar to the rejection sampling that we saw earlier. The difference is that it produces dependent samples, because if I reject, my next state is equal to my previous state. So in general, I will have dependent samples. But it can be shown that on average, the independent Metropolis Hastings accepts more often. So the expected acceptance probability, you can show that the expected acceptance probability is greater than or equal to alpha. So in the rejection sampling case, the expected acceptance probability was equal to alpha. So in general, we may accept more often. So let's go back to our truncated normal example. So we can do the same thing that we did here. Again, let's use the proposal of just sampling from a normal. We know how to do that. So we proceed by sampling x star from a normal distribution, and we set our new state equal to our proposed value if, and let's figure out what the acceptance probability is in this case. Alpha of x star given our current state. So that's just the ratio of these two terms. It's the minimum of 1 and p of x. It was our normal x star mu sigma squared times the indicator that x star is bigger than 0, divided by our normalizing constant, which is just 0 minus mu over sigma. At our current state, we have a similar we have to divide by the normalizing constant. Okay, so this is just the ratio of p of x star and p of xt. Now we have to multiply by the ratio of the proposal. So we said our proposal is just a normal. So we have the normal at xt mu sigma squared over normal at x star mu sigma squared. So you see some terms cancel here. The normalizing constants cancel. We have that the normal densities will cancel. Our current value is always bigger than 0, so this thing is 1. So our acceptance probability is just the indicator that our proposal is bigger than 0. Okay, so here's some samples from the truncated normal using an independent Metropolis-Hastings algorithm. So here are the crosses are my rejected samples, and these samples here are my accepted samples, and the size of the circle represents the number of samples equal to that point there. Right, because if we reject, we set our our new state equal to our current state. So we may have multiple values of the same sample here. Okay, so let's look at another example for the proposal. The random walk. So in this case, we propose a new sample, x star, by just perturbing our current state by some error. So we just take our current state and we add an error to it. So this epsilon is independent of our current state, and it has a symmetric distribution centered at 0. Typically, we choose this to be a normal distribution with some variance. Or if this is multivariate, this will be a multivariate normal with some variance covariance matrix. In this case, because the proposal distribution is symmetric and centered at our current state, then we have that this ratio here cancels out. So that our acceptance probability reduces to this term. So in Metropolis-Hastings random walk, the difficulty is choosing this sigma squared here. So the scale of the proposal should be as large as possible without incurring high rejection rates. So that means that we don't want it to be too large, because then we will get new candidates that are very far from what we actually want to sample from, and we'll reject too often. But we don't want it to be too small, because in that case, we won't explore the space enough, and we'll just stay around our current value. Okay, so let's see an example with a bivariate normal. This is just an example from this for demonstration purposes. Obviously, we know how to sample from a bivariate normal. But let's consider that we use a random walk Metropolis-Hastings to sample from the bivariate normal. As our proposal distribution, we use a spherical normal. So that just means our covariance matrix is diagonal with a common value on the diagonal. And it's centered at our current state. So in this case, we sample x star from our proposal, and then we accept with the ratio of our target distribution here. So in this plot, we have an example of sampling from a bivariate normal in this case. So the green lines here are our accepted moves, and the red lines are the rejected moves. So you can say, suppose we're at this state here, and we propose to move here, we accept. If we're at this state, we can propose to move up here, we reject. This is this circle here roughly describes the spread of our bivariate normal. So you can see that if so let's just draw a picture here. So we're at this state, we're sampling from a spherical normal. So if the scale of the spherical normal is too large, then we might get proposals which are too far away from what we want to sample from, and we'll reject. But if it's too small, then we'll see that we accept very often, but we don't explore the space well enough. We just stay around our current value. So in general, what's done in these random walk metropolis Hastings algorithm is people keep track of the acceptance, well, they approximate